Okay, this video I want to discuss the complexity properties of insertion sort. Actually, in the previous video, I already mentioned that that insertion sort is a very basic sorting algorithm. It's easy to program, and however, unfortunately, it is not the best algorithm that is that exists. So it has some merits, but the complexity analysis will show that the worst case is unfortunately quadratic. So we have a quadratic behavior of this sorting algorithm, and that makes it not very pleasant for us. So, however, we start the analysis of the complexity of insertion sort with the best case. This is often very easy to understand. What's the best case? And the best case here for insertion sort is just the array which is already sorted. So in this case, what we will see very easily by just stepping through the isolation is that it just checks whether everything is in place, and whenever it makes the first comparison, it already notices, okay, this element is already in the right place. So here it just makes this comparison and notice, okay, this is not the wrong order, it's the right order. So we can just move the yellow line, and this will be done for all elements. So in fact, we make n-1 many comparisons and 0 exchanges. So that's very nice. Yeah. So what we have after some steps, after 14 comparisons, since we started with 15 elements and 0 exchanges, is that this is already sorted. So that's quite nice. So insertion sort is very nice for us if we know that this array is already sorted. That sounds ridiculous, but in practice, you have to face the fact that an array is very often sorted or almost sorted, and you don't know what whether you always get a randomly ordered array, and in practice this is often not the case. So if you know that your array is sorted or almost sorted, then insertion sort is still an option. Yeah, although we will just notice in the next part of this video that the worst case of insertion sort is horrible, more or less. So the worst case is in fact just the array in descending order. So it's just the other way around. Yeah. So what happens in this case now? Well, actually, we will just make some steps and to see what's going on, and now after some steps we will end up here, and then we will dive into the analysis. Okay, now we have to make the inner loop for this element. So you see this is the bar, and this is the sorted part on the left hand side of the yellow bar. And what happens is, well, this is the minimal, this element is smaller than all of those which have been already sorted. As a consequence, it has to be swapped towards the beginning of the array, and as a consequence, to achieve this, it has to be compared to all of these elements. So we make a lot of comparisons, and in fact, with each element we make the same steps over and over again. We always swap each element to the beginning of the array, yeah, and this happens over and over again. And so if this here is the kth element, it's clear that we have to make k-1 many comparisons and k-1 many exchanges to put this to the beginning of this array. And if we sum this up, so if we have so for the kth element we have k many comparisons and exchanges, and if we sum all those comparisons up, then we have 0 to +1 +3 +4 and so on, until up to n-1. So this sum, if we sum this up, then we know that this is the formula that is the sum of all those numbers here. So it's n times n-1 over 2, and this is the number of exchanges and comparisons, and this is approximately n squared over 2 many comparisons. So it's a quadratic behavior. That's really bad and not acceptable. If you have a large array, you won't you don't want to insertion sort this. Yeah, so the worst case is really something that we really have to avoid in case of large arrays. So that's a bad news for insertion sort. And the average case, well, it's not really better. Actually, in the average case, so if we have something that is random, you will see the idea is very easy to understand for the analysis of the average case. In the average, well, in the best case we make 0 steps. In the worst case we make k minus 1 steps. And so in the average case we make k minus 1 over too many steps. So we have the same formula as here for the average case, but we divided it just by 2. As a consequence, we have approximately n squared over 4 many comparisons and n squared over 4 many exchanges. So now we have this simulation here. We run this until it's finished, and what we can see is it has 54 comparisons, which is roughly the half of 105, the worst case. Yeah, and we can just try it again with yet another experiment, and we have 57 many comparisons and less exchanges, because we often notice, okay, now it's the right order, then we stopped. So we always have less exchanges than comparisons. So you see for this 57, so we started with yet another one, yet another experiment, even 67, yet another one 45. So now this one was better. Here this is all close to the worst case, 88. So let's restart it, and yet another one, 95, 94, 56. Okay, that was better. 60. You see, it varies a lot, and and the average case is around the half of the worst case. Yeah. Okay, so that was the analysis of the complexity of insertion sort. Not the best sorting algorithm of this planet. There are better ones to come.